Okay, first thing I should say, and I will look into this 5th hour when my student teacher's teaching. Brittany pointed out that she did do the ed puzzles and I still gave her a 0. Yeah. So I said, hey, well, they're not submitted. And then I went to ed puzzle and they're done. So there's some disconnect that I don't know what's happening. I'll try and figure it out, but I will go on and unpunish you. Were you one of those, Tim? I can tell. I can tell. I can tell. I will fix it. But so we have what's called grade pass back now or something like that, where I just sync Canvas to the grade book. So I don't know why for some of you, there's no submission. I'll look into it. But anyway, I'll get it fixed. Okay, the lab yesterday. Raise your hands if you thought it went okay. Not the hardest lab we ever did. I see lots of yellow precipitates over there. There's a lot more precipitate than usual, which means you scooped up more powder than normal, but we'll live. I'm not too worried about it. All right. So this lab is actually me rewriting an AP test question into a lab. It was directly off of there. So we know the science behind it. We reacted PbNO3, which is basically just Pb plus 2, right? Tell your partner why it's okay that I didn't write the NO3. Do you guys know? There we go. NO3 won't react with the precipitate. It's a spectator ion. I can write it, but I don't want to write it. I want Pb. All right. Plus, I had Ki, but really I only care about I minus. And it made PbI2 solid. I'd put a 2 right here to make sure it balanced. Okay. So we dissolved the Ki, we added Pb, we got the precipitate, which we filtered, and we're ready to go. All right, there are some additional questions that Seth was asking about. So write a balanced net ionic equation, done. Explain why the reaction is best written by a net ionic equation. Kind of just said that, but will you just for a second tell your partner why this really is best represented as a net ionic equation? Ready, go. Oh boy. You didn't even get your hand sanitizer now? You touched your ring? That hand sanitizer, that makes me sick, so I'm not gonna get it. Sorry. Okay, so hopefully you said, because that's what actually happened. Right? Oh, don't be my house. Good. That's what actually happens in the solution. All the other stuff, just spectates. In my life, I married my wife. I met her in my Spanish class, and I can't name more than one other person in our Spanish class. And even that person wasn't important to me. There was only one other important person there in that class. We got married. Like, to me, that sounds really rude, but we got married. We have 4 kids. We've lived 20-something years since then, just mostly happy. It's not perfect, but that's, to me, that was the important part. Everything else was just there. And they moved on with their life. You think there's one person in that room that thinks of me? I doubt it. As confident as I am in myself, there's no way anyone in that Spanish class gives a crap about me. All right, here we go. So in the filtrate solution, well, what is the filtrate solution? You have to turn these in, so hopefully you're paying attention. What's the filtrate solution? All right. It's that. It's the stuff that wasn't filtered out. That's what came through. Okay, so underneath the funnel, forgot that word for a minute. Underneath the funnel is K plus greater than, less than, or equal to NO3. Justify your answer. Okay, I want you to think about what you did with your lab partners and think, all right, can I explain? Yesterday, that whole thing we went to was like, about how important it is to justify and have information to back up your justification. Pick your answer here. Is K plus greater than, less than, or equal to NO3? Justify your answer. Will you do that with your partners right now? Just talk about it. We'll talk about it together, but please talk to someone about it. Mimi, I want you to talk to Keely. That is unfortunate. All right, well, you can sort of look up there and think through it.
I tried to get on the
Oh, I did see. It's at the very top of everything.
I tried to get on like 5 minutes.
Yeah, I got an email, but I was in that conference and there's nothing I could do about it because I wasn't in the room. And I couldn't text her to start it either. Sorry. When you log into Zoom, anyone does, and I'm not on, I get an email that someone's waiting. And then I can't do anything about it. Okay. Does anyone have an idea that they're willing to share? Go ahead.
It would be less than because the potassium is part of the limiting reactant.
Okay. So says less than because it was part of the limiting reactant. Who agrees with that? Anybody? Okay, that's a great answer. Does anyone have a different answer that they want to share? Go ahead.
Acid was greater because in the fully balanced equation there was 2 NO3.
Okay, and okay, and 1 PbNO3 too. Okay, that's valid. There's a problem with that one though, because we do have 2 Ki, and then okay, but we have PbNO3 2. So there's going to be 2 and 2. It's okay. I like that you took a guess and were able to say it. All right. So Davis, say it one more time. Okay. It's part of the limiting reactant. By definition, the other one is in excess. Okay. So it should be less than. All right. Part C, you can't do yet. Calculate the number of moles of precipitate produced. Can't do that yet because we have to weigh it out first, right? Part D, calculate the mass percent of iodine in the tablet or the sample. Can't do that yet either. I hope we're okay with how you would do that though. Mass of, you got to be sort of careful here. We're going to, when we find the mass of the filter paper and the stuff, we subtract it out, and we're really finding the grams of PbI2 solid, right? We do not compare this to our initial mass. What do we need to do first? It's tricky. They can still be friends. If I know the grams of PbI2, but I want to know the grams of just I minus, I can do that, can't I? I'd have my grams PbI2. I'd have my, this is what like my sample or like my answer. Then I'd have the molar mass. Okay, we'll just go like that. All right, per 1 mole, PbI2. Tell your partner what comes down here. Mole PbI2. For every one of it, what would you have up here? Good. 2 mole of I minus. What would be down here? 1 mole I minus. And what would be, what's up here? What's up here then? Grams of I minus. So it's tricky because on the AP test, this is where people got their butt kicked. They're like, oh, I know that answer. It's right there. But then you do the math and you end up like 4 times the amount recovered. You're like, well, that's weird, but that's what I got. No, we first have to isolate I minus because that's what we cared about. This was the tool to separate it. And then we use math to find out what it was supposed to be. That gives me my grams of iodine. to find its mass percent, then I have to divide by the total mass of the sample. You okay with that? Okay, tricky. Hypothetically, in another trial, you dissolve a tablet in 55 milliliters of water instead of 50. Predict whether the experimentally determined mass of percent I would be greater, less than, or equal to. Ready, set, fire away. Discuss that one. This is a really super good question. All right, don't forget, you two talk to each other. All right. Anyone willing to say that they think it's greater? Greater, full send. I have one greater. Anyone less than? I have 1.5 less than. Who thinks equal to? Okay, the answer is equal. All right. So here's my question. Is water part of this reaction? No. There's plenty of water for all this to dissolve. So it wouldn't matter. I mean, if we got like a very small amount of water, it would matter because it wouldn't all dissolve. But we've got plenty. Water is not part of this. When you learn later in chapter 17, you'll have a better answer to this. You'll say KSP is independent of the amount of water present, which is what this is asking. You just don't know that yet. But as long as we have a soluble substance, especially NO3, water is really not part of the reaction. It's the place it happens, but it's not part of it. Okay. And then you can get this number, your percent error, after you have the data. We'll probably do it tomorrow. Should be nice and dry by then. As I looked this morning, they look pretty dry, but I want them to crumble a little bit better. As they dry, they usually they look like a desert that had water and all breaks. It separates. I don't know. I can't talk. Anyway, Seth, did I answer enough questions? Okay. Then that was what I had. I think we're done. Just kidding. Wouldn't that be fun? Okay, some of you should check your grades. They're not super hot. Once again, I'll fix the whatever, but I believe we were just talking about acids and bases, and then I went on a road trip to Provo. So let's pick that back up. I don't know what direction it is. Don't stare or you'll get. All right, we already said that. Okay, let's test yourself real quick. Test yourself. Are you ready? On your paper, it's not graded, so relax. On your paper, just somewhere where I can look, write as many strong acids and bases as you can without looking at your notes. You sound better. You feeling better? Sweet. Okay, as many as you can. So try and write as many of them as you can. Strong acids and strong bases. Tim, good. Tim knows there's 7 of them. He hasn't written all 7, but he knows, hey, I got to get to 7. When in doubt, put a chlorine in it.
Wait, is this right or am I doing this wrong?
Those are 2 strong bases. Quiz yourself.
I got 2. That's all I need.
B time? Yeah, pretty much every day. During B time? I was in that room for like 10 total seconds. Yep. Hey, was I in B time all day today? Witness. All right. It's okay. Strong acids without looking. Anyone? HCl, good. We should never forget that one. Okay, what else? HClO3, good. Anyone? HClO4. H2SO4, good. What do we got left? HNO3. We're at 5. Hi. And HBr. Starts with an H. There you go. Started with an H. Anyone have all 7? You want to flex on your friends?
I'm just proud I got 4 strong bases.
No one had 7? Okay. Oh, you did. Okay. Payne had 7. Strong bases.
Guess what?
LiOH. Okay. What? Okay. And one more. Yep, I think we got them. Yeah. We are cool like that. That's supposed to be I was looking away, sorry. Okay. Now, the harder part, assess your partner's ability to tell you what a strong acid is. I have no idea.
They literally just get up and walk.
I'll go tell him. All right, Miller says he's sorry. It could definitely be this class too, by the way. Okay, are we ready? Who thinks, no one has to say anything, just raise your hands. I won't embarrass anyone, but who thinks their partner had a pretty good explanation for what a strong acid is? Ready? Raise your hands. Okay, so wow. If you felt like it went okay. Okay, strong bases, you don't have to say because it's the same thing. You just put in the word base instead of acid. Strong means they don't hold on to each other very well, right? They completely dissociate to make strong electrolytes. Okay, I feel like I've said too much. All right. I think we ended about right here. Did we not? Right here? Okay. When an acid and a base react, there's a name for that type of reaction. It's called a neutralization reaction. Any guesses why we call it that? Yes.
Then neither of them are either acidic or basic.
Perfect answer. I loved it. Because once they react, there's no more acid and no more base. There is a salt, which does not affect the amount of H plus or OH. And then there's water, which is HOH. So it becomes neutral if you put equimolar or isomolar. That's on your test, by the way. I don't know what that is. You can. I can't hit that note. What? There we go. So anyway, we neutralize bases with acids. On your test, I got disrupted by squealing. I use the term isomolar. Iso means same, molar means just the concentration. So it asks, it's a trick question. I'm just telling you right now, what will happen if you add isomolar amounts of A and B? Like, or it says, what's the limiting reactant? And you'd say, not today, Davidson. There isn't one. Or both of them are, whichever way you want to put it. Okay. All right. Fair enough. Neutralization, acid base become neutral. All right, there are some easy ones, which is just when there's clearly an acid and a base and it makes a salt and a water. Pretty easy. And I believe we said this the other day, that the net ionic, that's a super good rectangle right there. The net ionic for an acid-base neutralization is H plus OH goes to HOH. Did we say that? Okay. All right, I think we're ready for new stuff. Okay. Now we got to be careful. This part is very confusing. So please be patient. It is tested, but we can get through it together, I hope. I just prayed to the chemistry gods. We should be okay. But I'm moving farther away from my friend Tim. Oh, my shoulder here. All right. So that's a cool dance. All right. There are some red flags. The red flags are when you have a weak acid or base involved, or there's a solid involved. And this will come up to be a huge problem in chapter 15 and 16. But for now, that's kind of on the low level of stress. Solid involved, this is going to be a big deal. And then is a gas involved. Gas forming acid base or whatever reactions are really tricky for you to remember. Their net ionic equations are weird. So just stick with me and we got this. So here we go. I already said that. All right, is that going to erase everything? It does. I won't do that. All right, if, and you don't have to write all this down. You are welcome to, but you don't have to. If I take a weak acid, there's something different right here. Anyone willing to tell me what is different right here than normal? It's a liquid. That means it's not aqueous, or it means it's not dissociated. So, all right. NaOH, though, is a strong base. So here's my reaction. In this reaction, sodium acetate is formed and water. Well, that seems fair. It's just a double replacement neutralization reaction. So the complete molecular or ionic would look like this. You would include this together this time instead of breaking it apart because it's a liquid. It's not aqueous. But you would have Na plus OH minus still as ions because they were aqueous. Then you have your arrow right here. It makes sodium acetate, which I would look at my solubility chart and I would know acetate never is a solid, right? Not a solid. It's never a precipitate, I should say. All right, so then it stays aqueous plus water, which is a liquid. Then to go from complete to net, you cross out anything that was exactly the same on both sides. And this time it was only the Na plus. Because the acetate on one side of the arrow is an ion, but the acetate on the other one is part of a weak acid. You think this is a lot to remember. Well, that's true. It is. It is a very large amount of stuff to remember. All right. So the lesson there, if you have a weak acid involved, and how will you know if it's a weak acid? It's not a strong one. That's why you got to memorize the strongs, because it could be like the weirdest words you've ever seen in your life. You're like, I don't know if that's a strong acid. Well, if it's not one you memorize, then it is a weak acid. Okay, then you really only eliminate one spectator ion, and it comes from the salt at the start. Let me see if I have another one for practice right here. Okay, I don't yet. Okay, I'm going to write another example. It'll be shorter, like less stuff to write. You ready? The shortest weak acid to write is called HF, hydrofluoric acid. It is a weak acid, even though it's extremely reactive. That's different. It's a weak electrolyte or weak acid. All right, plus, I don't know, what do you feel like from family 2? It's got to be towards the bottom, sorry. Barium. All right, barium hydroxide. Is this a strong base that you memorized? Yes, it is, which means this would be aqueous. Okay. Whoa, that was weird. What are the two products just by switching? Barium fluoride and water. Did we learn anything about fluoride? It was never really on a list. It's never on, it's not on the insoluble list. So if forced, we would assume it is soluble. Okay, will you write? You can write the complete one, that's fine, but at minimum, write the net ionic equation or reaction for this. When you are done, will you just quickly assess with your lab partners? See what you guys think. On the AP test, it will give you something like this and ask you to balance the net, and then it will also ask a question. So that's what you'll get on the chapter 4 test. This is really similar to exactly a question on the test. Okay, talk to your partner for 30 seconds. Let's move on. All right. So when you look at this, you want me to write the whole thing? Okay. I was not going to, so I'm glad you asked right in time. Liquid, tell your partner, do I keep it in the whole thing together or apart? Together. So HF liquid plus, if it's AQ, tell your partner how I'm going to write this. I'm going to break it up, right? BA plus 2 OH minus. All right, so that's the reactants. Over here, it's aqueous. So do I keep it together or break it apart? Break it apart. AQ means chop it in half. So I have BA plus 2F minus plus, if it's a liquid, what do? Leave it together, right? HOH liquid. So the next thing I do, I look at this whole row and I look for anything that is exactly the same on both sides of the arrows. And it is only what? It is only barium. So which is /R the spectators, that would be Ba plus 2, right? The net ionic equation would be HF liquid plus 2OH minus goes to 2F minus plus HOH liquid. And I do have a problem right here. What's my problem right now? It's not balanced. So I'm going to need a 2 here and a 2 here. If you balanced it at the start, you would have been okay. Like you would have seen that. You would have brought it down. You can do it start, middle, end, doesn't matter. I don't like that looks. Okay. Okay. How many had that right? Raise your hands. Ooh, that's a small amount. What am I doing wrong?
I just missed twos are so confusing.
You what?
I just missed coefficients.
Miss the coefficients. Case, is that what you said?
Is there a reason we need all the twos?
You can go 1, 1, 1, 1 if you feel like it. Absolutely.
Sweet, so I did it right.
Yeah. There's nothing wrong with that. Other questions? Same question? Okay. Yep. If they all end up to be the same, yeah, you can eliminate all of them. It's fine. Okay. Haley, good? All right. Now, we're going to move on, but we'll come back as well. Okay. So we're going to layer more on, but then we'll come up and review all of them again together. But the next is really tricky. And the AP test loves the hard parts of AP. Like there's hardly any questions ever that say, what's the name of NA? Like that'd be money. I could pass that test. You can get up to 8 college credits for this class. So they make it kind of hard. And they love gas forming reactions because they're tricky. All right. These metathesis or double replacement reactions do not give the products expected. Okay, there's only a few of them. The expected product decomposes to give a gaseous product of carbon dioxide or sulfur dioxide. All right, and that there should be also, or, oh, that's highlight tool, not pen tool. Or hydrogen sulfide gas. These are very specific reactions. I don't know, they're tricky.
Are those the only ones that actually do it?
That we're going to worry about, absolutely. Super red flags here. If you see the following things, do you see all these things I have a black box around? If you see them in the reaction, you got to think, oh, Davidson said something about these. Oh, he said they're a pain in the gas. All right, so here we go. I know that was not appropriate. Calcium and then CO3 is called what word? Carbonate. Who's ever mixed baking soda and vinegar? Raise your hands. All right, baking soda and vinegar bubbles because you're adding an acid to a carbonate. This is not exactly baking soda and vinegar, but it's the same idea, an acid with a carbonate. So if a reaction that I ask you to finish and write the net ionic form has the word carbonate in it, it's a red flag and you need to know that there's going to be a gas produced. All right, HCO3. What's that one called? Hydrogen carbonate. On the multiple choice of the test, I've done this like 8 out of the last 10 years. I forgot to warn you that hydrogen carbonate is often called bicarbonate. So you got to that one question, and I think it was Brown. I was super proud of her. She wrote like, it's hydrogen carbonate. Was that you? I'm pretty sure it was, because the hydrogen carbonate wasn't there, bicarbonate was. I gave everyone credit for that problem, so don't stress. But hydrogen carbonate or HCO3 is often called bicarbonate. All right, SO3. This goes back a long time. Sulfite. Good job. It's ITE at the end. If you see sulfite, it's going to produce a gas. The good news is that these three are super similar. One says carbonate, the other one says hydrogen carbonate. Both of those end with a CO3, right? And then this ends with an SO3, which is kind of like a CO3. Okay, the top three are all the same idea, I promise. Okay, the bottom one, what's S minus called? All right, sulfide. So those four anions in one of these reactions, they're red flags. Now, there is a huge, how do I put it, qualifier before you actually have to worry about this. These rules only matter if you're reacting them with an acid. Because we can react carbonates with other things and they don't do this. But if I take any of these four anions as part of something and mix them with an acid, I'm going to get a very specific type of reaction. Okay. So far, at least you're awake. Okay. Now, carbonates with an acid always make a salt. Carbon dioxide, I don't want to write it, I'm just going to scribble, and water. What's that? If I add a carbonate to an acid, that always happens. I make the salt and carbon dioxide and water. I will come right back to this page in a second. I will come back, so don't panic. But if I take Na2CO3, and I'm just going to put HCl because that one's so easy to write all the time. It makes NaCl, which is a salt, right? Plus, if we didn't know what we were doing, we would just say H2CO3, right? H2CO3. That would be the double replacement reaction that we would expect. And it's sort of true. This substance right here is called carbonic acid, and it's not stable. It doesn't want to stay as carbonic acid. It wants to decompose into water and carbon dioxide. This is how a lot of your drinks get carbonated. They store carbonic acid under the conditions where it stays the same. Then they put it into a drink, and you're not drinking carbonic acid, you're drinking what as it broke down? Water and bubbles. Breaks apart. Okay. It came once again because I took a carbonate, reacted it with an acid to form a salt, and then this that breaks apart. Go ahead.
So that just makes carbonated salt water, that reaction?
That one would, yes. It tastes delicious. Okay, now think about this. Well, I don't want to go there yet. I need to come back to this slide because I promised you I would. We'll get there in a second. Okay, hydrogen carbonate doesn't do anything different. It breaks down into a salt plus carbon dioxide and water. It does exactly what we would think it does, except for the carbonic acid, H2CO3, breaks apart into H2O and CO2 gas. All right, will you look with your own eyes and then tell your partner the similarities? That's ugly. That's just terrible. The similarities between this reaction and the two we just did. Describe it. Similarities. Maybe the differences too. What's similar? What's different? All right. It was short. I didn't give you much time. One way they're similar. They make water. They make a gas. Anything else? They make a salt. Good. They're almost exactly the same. We literally changed one thing. We changed an S to a C or a C to an S. It's exactly the same because it was CO3, now it's SO3. It still makes a salt. It was CO2, but now it's SO2. It was carbon dioxide, now it's sulfur dioxide. It made water and it made water. It's no different except the C is an S. You with me? We would not put this in our drinks. This would be really bad for us, right? So carbonate, hydrogen carbonate, and sulfite are the same basic chemistry. Okay, sulfide is different. This one is on the test, very common, the AP test. It will give you a sulfide. Usually it will give it to you in a solid form. It'll say, you're going to react sodium sulfide with sulfuric acid. Account for how you would do this reaction. And you're like, what? Well, what they are wanting to elicit from you is that you know hydrogen sulfide smells terrible and can kill you. So in the answer, they're looking for the word fume hood. You'd say, I would add that to the acid in the fume hood, because that stings. Who's been to Yellowstone? It stinketh, right? Who's been out to Corinne, the west side of Corinne, the hot pots? They smell bad. The reason why is because there's sulfur in the ground. It's being heated in a little bit of acidic water, and it produces sulfur dioxide gas. Or not sulfur dioxide, that's one above it, sorry. Hydrogen sulfide. Okay, so when we have sulfide, IDE, we make the salt and we make hydrogen sulfide gas. This stuff is really bad for your nervous system. So you should always make it in a fume hood if you're going to do it. Now, we've been talking about net ionic equations for a few days, right? So now that we know these, we're going to tie it into net ionic. I'm going to go to the next slide, which I wrote this one out. You with me? Okay, in this problem, it said, well, I just made it up. Let's say for right now, this is aqueous. HCl, strong acid, so that's aqueous. NaCl, is that strong or weak electrolyte? Strong, it's aqueous. H2O is water, which is a liquid. CO2 is a gas, which gets a G. So far, okay? Now, this is the whole thing. Let's break it down. Remember, I'm saying this didn't really exist. So now I'm going to write the complete ionic. Anything AQ, I'm going to break up. So 2Na plus CO3 minus 2. That comes from these parts. You okay with that? I broke them up because it had an AQ. Plus H plus Cl minus. I broke them up because it had an AQ. Then my arrow, NaCl, also aqueous, so Na plus Cl minus. And then my arrow, not my arrow, sorry, another plus sign. That was stupid. Oh, you gotta be kidding me. Fine. Then plus H2O, I keep it together because it's a liquid, and CO2, I keep it together because it's a gas. I only break up the things that are aqueous. Then I go to town with my red X's and get rid of anything that is exactly the same on both sides of the arrow. So tell your partner what things are exactly the same on both sides of the arrow. No.
But with the two, the NA, make it so they don't.
No, there would be a 2 here,
There'd be one NA.
and there'd be a 2 here, and a 2 here, and a 2 here. Like if I would have balanced it. Okay, so I am going to eliminate sodium, right? Because it's an ion on both sides of the arrow. I'm going to eliminate chloride because it was the same on both sides of the arrow. So really, I have CO3 minus 2 plus 2H plus goes to H2O plus CO2, and I should put the liquid in the gas. Fair enough. Okay, I'm going to change one tiny thing here, and I want you to tell your partner what that would change. I'll go for that here. We ready? I changed that to a solid. Will you tell your partner what that changes? I changed that to a solid. What changes? All right, what I want you to do right now, I want you in large enough font that I can see it. I want you to put the spectator ion or ions on your piece of paper and hold it up for me. It's got to be big enough for me to see right now. Now that that's a solid, what's my spectator ion? Write it big enough for me to see and then hold it up if you would. Okay, keep holding it up. Good, 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 good. Well done. Nice. Good job. I need to get better glasses. Now there we're talking. Those fonts are very legible. Good. Okay, good. All right, I didn't see anyone that was wrong. That's a good sign, right? Now, if you're like, wait, I was wrong. Maybe I didn't see yours. So this is what changes. If this is solid, then it would have stayed together the whole time, right? Na2CO3 solid, which meant that now this did change. I'm going to use a red X to get rid of a red X. That was satisfying. It went from the Na2CO3, and I had this extra over here to Na plus. It was no longer a spectator. It went from the solid to an ion. That is a change, so that would be indicated. So only chlorine would have been the spectator ion. You okay with that? All right. What is this? This is a beautiful picture. Yeah, I don't know. You don't need to write that, but it's cute. Okay, here we go. Let's do some practice. I have so much here. So let's go with CaSO3. So calcium sulfite plus, what's your favorite strong acid? HCl again? HClO3. I'm okay with that. Now that will be aqueous. Let's say our calcium sulfite was delivered as a solid. And then you take it away from there. We're out of here in 2 minutes, aren't we? Okay, so maybe I'll do this for you. Actually, that's as much as I'm giving you, which I feel like is a lot. All right, I'm going to move on in 20 seconds. I know there's no way on earth anyone's done, but I might as well like get you the answer while we're here. Oh, you'll hate me. That's fine. I'm married to a super good looking woman, so I don't even care anymore. My kids like me a little bit. There's 3 more ed puzzles I want you to watch. They're 100% for your own benefit, I promise. I made them fast forwardable though. This time, if you get it, you're like, all right, I'll go to the questions. Okay, here we go. I got to go fast. They're for the math we're going to do. All right, since this is a solid, I'm going to go all the way down here. This was aqueous, so I'm going to say plus H plus ClO3 minus. You okay with me so far? This is aqueous, so Ca plus 2 ClO3 minus plus this breaks down into H2O and SO2, correct? So what's my only spectator? ClO3, so I better include the others, plus H plus goes to Ca plus 2 plus.
Because it was only 1 millimeter of